Today we're going to talk about related rates. And with related rates, you're going to talk about equations. We're going to talk about solution strategy and simulated related motion. So when you start solving related rate problems, what you have to do is to, first of all, to understand the problem. And that means to see what the rate is that's changing. And you have to read the problem possibly a few times in order to see what the rate is that you're looking for.
Mr. Bob Gorski, please call 7002.
The other thing,
Bob Gorski, call 7002.
next thing that you should do is to draw a diagram. And that helps to visualize what you're looking for. And that really does help. I strongly suggest that you draw diagrams for these problems. You then have to find the right formula, most likely a geometric formula. But those are the ones that you know. Area of a circle, area of a square, area of a triangle, simple geometric formulas. We then differentiate both sides with respect to time. And remember that because you're differentiating with respect to time, that it has to be done implicitly. You do remember implicit differentiation, I hope. After you differentiate, then you're going to substitute values into your derivative. This substitution happens after differentiation. The only substitution that happens before differentiation are those numbers that are constant. You can make substitutions for things that are constant before differentiation, but after differentiation, you will have to make some substitutions. After you solve the equation, then you have to make sure that that the answer makes sense and you interpret the solution. So let's try a couple. As in the optimization problems, I can show you a dozen problems, and each will be solved differently, but they're all rates of change problems. There's no one way to solve a related rate problem. So we have here a radius of a sphere is increasing at a rate of 2 inches per minute. And you want to find the rate of the volume when r is equal to 6. So what do you have to start with? Well, you start with a sphere. And you start with the volume of you want the volume. So you're going to start with the volume of a sphere, which hopefully you know is 4/3 pi r cubed. And you want to know how fast the rate of change is, how fast the radius is increasing. So here's your r. So you take the derivative on both sides. dv dt, remember everything is taken with respect to time, equals 4 pi r square dr dt. That's where the implicit comes in. That's where your implicit differentiation comes in. Since nothing was constant, I can now substitute in my 6 inches. So we also substitute in, we also substitute in the 2 for the r. So we have dv dt equals 4 pi times 2 square times 6. And whatever that rate of change is will be your rate of change of the volume. So that's 4 times 4 is 16 times 6 is 96 pi. And that would be inches cubed per minute. So that's your first related rate problem that hopefully that gives you an idea of what we're going to do. I have to take away the smart ink. Okay, so here's our second problem. Oh, sorry. We have a hot air balloon rising from a level A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising? So we have our balloon. And you can get creative with your drawings. As you can see, mine are not that great, but you can still work on it. And it's the rangefinder. It says that the rangefinder, here's your diagram. We have a right angle. The rangefinder is 500 feet from the liftoff point. We're not going to put in the pi over 4 quite yet, but we do know that the angle is increasing. This is our angle, and our angle is increasing, so our d theta dt is 0.14 radians per minute. And that's when the angle is pi over 4. And we want to know how fast is the balloon rising at the minute. So we want to know dy dt. We're looking for dy dt. So what formula are we going to use here? Well, anytime you have an angle, we have to use your favorite. We have to use trig. Now, we don't have our hypotenuse. So what trig function are you going to use? That's right. We have to use tangent. So we have tangent theta equals opposite over adjacent. So it's y over 500. And then you take, now that you have your formula, now you have to take the derivative. So we have secant squared theta d theta dt equals 1 over 500 dy dt. Okay, now what happens next? Well, now you can start putting in everything that you wanted to put in. We know our angle is pi over 4, so you have secant squared pi over 4. Our d theta dt is 0.14, and we have 1 over 500 dy dt. Okay, so we could add, we're going to finish the work up here. Secant pi over 4. See if you remember that one before I put it up there. Anybody, put your thinking caps on. So what is it?
Joshua
Think it's squared. You're right. It is 2.
Report to the attendance office in the Corps. Joshua
Times
McNichol.
0.14. We're going to multiply both sides by 500, and that equals dy dt. And when you multiply that together, that's 1,000 times 0.14, so that's 140, and that was feet per second as your change in the height. So remember, anytime you have an angle, you're going to use a trig function. You have to use a trig function. Okay, one more, and this one involves a cone. Now, normally when you involve a cone, you have to, don't make me laugh, you have to use a ratio. And this says a water runs into a conical tank at the rate of 9 feet cubed per minute. The tank stands point down, and it's running in at 9 feet cubed per minute. It has a height of 10 feet and a radius of 5 feet. How fast is the water level rising? So you want to know dh dt when h is equal to t. H is equal to 6, rather. Now, one thing about a cone, this cone is standing straight up and down. it's at 90 degrees. We're not going to shift it. We're not going to tilt it. We'll leave that for when you're taking calc, higher levels of calc. But what we have, as this fills up, what we have are similar triangles. So if you remember, similar triangles have equal angles, but their sides are in proportion. So we will have that the ratio of your radius to your height will always be the same. And that's the same as 5 is to 10, which is 1 is to 2. So that's going to be the height, the ratio throughout the entire problem. So now we have our volume of our cone, which is volume equals 1/3 pi r square h. Now I have two variables there. I don't want two variables because that means that I would have to do some type of product rule, which I really don't want to do in this type of a problem. So I have to substitute. Well, I have here that r over h equals 1/2. So which one do I want to solve for? Well, I want dh dt, so I want to get rid of the r. So r is equal to 1/2 h. So I'm going to substitute that in. V equals 1/3 pi times 1/2 h squared times h. And when you simplify, you have 1/3 pi, that's 1/4 h squared times h, so that's 1/4 h cubed, which is h pi h cubed over 12. Now I have one variable. And if I take the derivative, dv dt equals, bring the 3 down, so that's 1/4 pi h square dh dt. And I just have to plug in all my numbers now. Oops, sorry. I thought I had another screen there. So my dv dt is 9 equals 1/4 pi. H is 6, so 6 squared is 36 dh dt. So this is 9 pi, and I have a 9 over here, so dh dt equals 1/pi, and the units would be feet per second. Okay, so those are 3 problems with related rates just to get us started, and we're going to try those 3 different types of related rate problems in class. Tomorrow, we're going to go through a lot of these problems, so take a look at the video again if you need to, and we'll work on these problems again in class. So hopefully you learned what to do with these. I'm not asking you to do the problems at home by yourself. That's what we're trying to do here. We're going to work on these together as a class tomorrow and the next day. Thank you very much for watching.